Question 16 involves something called Cavalieri's principle, or I suppose if you're Italian, Cavalieri's principle. Again, I think it's in the Springboard book somewhere, but anyway, basic concept is if you're finding the volumes of two different shapes, you can basically, I think it's easiest to see with any kind of prism type shape. If the base areas are the same, you're stacking the same number of blocks on top of each other from the bottom to the top. If the base areas are the same and the heights are the same, the volumes are going to be the same. So volume of this would be 20 times 10 if that's the area of that pentagon, and the volume of this is going to be 20 times 10. Cavalieri's principle goes a little bit further than this, okay? It doesn't assume necessarily that the shapes have the same bases from top to bottom. But what essentially Cavalieri's principle says is, as long as any cross sections from one shape to the other are the same, the volumes of the shapes will be the same. Okay, so in this case, if you do a cross section across the bottom, the base area is going to be equal to that base area. If I did a cross section, 1 unit up, and compared it to a cross section 1 unit up, those areas would both be 20. If I did a cross section here and a cross section there, those cross sections would both be 20. Anyway, the point is the cross sectional areas starting at the bottom all the way up to the top will be the same. And again, this implies that they have the same height, okay, because you can't compare cross sections across two shapes if they're not the same height. But technically, and you'll see this in 17, the shapes could be changing as they move from the bottom to the top, but as long as those cross sections remain the same for each step along the way, the volumes are going to be the same. So anyway, over here, that's all we're trying to show. We're just trying to show that the cross sections are the same. These things have straight sides, so we're basically just trying to show that the area of the ring, which you might remember from geometry is called the annulus, we're trying to show that the area of this ring, which would be the cross section area all the way down, since it's vertically oriented, is equal to the cross-section area here. Of course, the cross-section area here is just a circle that has a radius of radical 3. And again, since the heights are the same and the cross-sections would be the same from the base to the top, we just have to show that the ring area is the same as the solid circle area. So anyway, so all we're going to need to show here, and I think that inner radius there is r, if I remember correctly. So anyway, we've got an inner radius of r, we've got a big radius of 2r. So we're going to take the big circle and we're going to subtract the little circle. So the big area would be pi r squared, right? Pi times the radius squared. So it's going to be pi times the radius squared. And then we're going to take pi times the radius squared, and radius just r for the little circle. And so that's going to be 4 pi r squared minus 3 pi r squared. Oops, sorry, just minus pi r squared. Getting ahead of myself there. And that's equal to 3 pi r squared. So the area of one of those cross sections in terms of r is just 3 pi r squared. Okay, so now I just need to show that the area of these cross sections will also be 3 pi r squared. Okay, so the area of these cross sections, of course, it's going to be pi times the radius squared. The radius here is r radical 3, and we're squaring it. So that's going to be radical 3 squared, which is 3 r squared, which is r, and that's going to be 3 pi r squared. So what have I shown here? I've shown that the cross-sectional areas, again, because the heights are the same for these two shapes, all I have to show is that any cross-section of these two shapes has the same area, okay? The ring has an area of 3 pi r squared. The solid circle has an area of 3 pi r squared. Since the heights are the same, any slice you make across those two shapes is always going to have an area of 3 pi r squared. So by Cavalieri's principle, those two shapes will have the same volume.